The first speaker is Stefan Willitsch from University of Basel, and he will tell us about the ion neutral chemistry and ultra low energies. And given the fact that I see this in this enormous clock in front of us, I think I don't have to remind the speakers about the time. So please, welcome.
Okay, thank you very much. Can you hear me? No? No, very good. So thank you very much for the kind introduction, and I'd also like to thank the organizers for the invitation. It's a pleasure to be here today and to be given the opportunity to share some of our recent work with you today. So the topic of my talk belongs to a rather young field, which is the study of chemical reactions at energies or temperatures at about 1 Kelvin or much lower. And why would one be interested in studying chemical reactions in such an extreme regime? Well, it turns out that one can study rather exotic chemical processes there. And since, well, the particles are so cold, they are very slow, and this means that the de Broglie wavelengths of these particles becomes very long. So this also provides opportunities to study collisional quantum effects that also influence the chemical reactions. And when things are so cold, then very fine details of the interaction potential between the particles becomes very important, and so this is also a very good environment to explore fine details of intermolecular interactions. But it also turns out that the methods that are developed in this context are also very apt to indeed study and control chemical reactions, namely by controlling the quantum state of the reaction partners and the collision energies. One can turn many of the control knobs that are interesting for a chemist. And there are also techniques for selecting shapes, specific shapes of large molecules, and then study the influence of these shapes on the chemical reactivity. And in the end, this allows one to unravel fine details of chemical reaction mechanisms that were not accessible with previous techniques. So in a nutshell, this is our motivation for studying chemistry at very low energies. And our interest actually lies in studying ionic processes, so ion-neutral reactions in this regime. And I will start by telling you a bit about the experiments that we do and the methods that we use. And then I will introduce some model system and discuss the chemical processes and mechanisms that we observe in these model systems. I will also talk about the dynamics of these processes. And I will then move towards new developments where we improve our experimental techniques to study these processes with an even higher energy resolution, and where we also start introducing molecular ions and neutral molecules into our experiments. Good. So all of what I'm going to talk about today only became possible with technological innovation of the last few years, and that is the development of combined ion atom experiments, which rely on the combination of a trap for ultra-cold neutral atoms with an ion trap for cold ions. And these types of experiments were first proposed some 15 years ago by Robin Coté and subsequently by Winthrop Smith. The first experimental implementation came by Willitsch about 6 years ago, and since then a broad range of experiments like these have been implemented all over the world. So it has become a veritable field of its own. So in our case, in our specific experiment, we do have a magneto-optical trap. So this is a trap for neutral atoms in which optical and magnetic fields are used to cool and trap neutral atoms. In our case, it's rubidium atoms. And sandwiched in between this mod, we have an ion trap. So this is an electrodynamic trap. It uses radio frequency fields to confine ions in the center. So like the atoms, the ions are cooled by laser cooling. And when one puts ions in such a trap, and our favorite ion is calcium plus, so this is an ion that, an atomic ion that can suitably be laser cooled, then the ions in the trap at very low temperatures undergo a phase transition to an ordered state. And this ordered state is called a Coulomb crystal. And depending on how many ions you have in the trap and how you run your experiment, you can have single trapped ions, which you can see here, or a string of ions, or these large spheroidal shapes, which we then call Coulomb crystals. So what you see here are fluorescence images of the ions. So the ions are being laser cooled, so they scatter photons all the time, and the fluorescence is then captured by a camera, and this gives us these images. Now, these crystals, these have very intriguing properties. Well, obviously, they are cold, usually millikelvin, but if you try hard, even microkelvins are possible. You can keep them in a trap for a very long time, easily up to hours. And since one can obviously observe single particles, one can also address single particles, and this enables to perform experiments which are very, very sensitive. And this is also a key feature of the experiments that we do. Good. So now, good. So what kind of processes can one observe in such systems? So one of the first systems we looked at was, well, the simplest possible one in our setup. So we combined laser-cooled calcium ions in the ion trap with ultra-cold rubidium atoms. And what we see in the experiment is this. So we have a Coulomb crystal of calcium ions, which is immersed in a cloud of ultra-cold rubidium atoms, which you can see here in the background. And what we then usually do is we block the fluorescence from the rubidium atoms and just concentrate on the calcium ions and see what they do as a function of time. And what we see is that this crystal starts to shrink over the time scales of a few minutes, so the calcium ions disappear. And one can also see a characteristic flattening of this crystal here, and this comes from the generation of other ions. So as some sort of chemical process seems to be going on, product ions are produced, and they are sympathetically cooled into these crystals, and this can be seen by this characteristic flattening of the remaining calcium crystal. So we have some chemical process here which produces product ions, and the first question is, of course, what is this chemical process? So in order to establish that, we can turn our ion trap into a mass spectrometer and record a mass spectrum. And before the reaction, we just see a single resonance in this mass spectrum, which corresponds to the calcium ions which are there. But after the reaction, we see 3 peaks. And we assign these peaks to the formation of rubidium ions, calcium rubidium ions, and rubidium 2+ ions. Now, the rubidium ions was a product that, in fact, we expected, right? So rubidium has a lower ionization energy than calcium, so one can imagine that the charge transfer happens between the 2 species, producing rubidium+. But these molecular products were actually quite surprising. That was quite unexpected. And it was quite unclear by what mechanism these molecules can be produced. It becomes clearer when one has a look at the potential energy curves, which were calculated by our theory collaborator Olivier Doulieu and his team in Paris. And one starts to understand what is going on in the systems by realizing that the lowest collision channel, this is when a rubidium atom in its ground state collides with a calcium ion in its ground state, is not the lowest molecular state of the system. So what happens is we come here on this curve, but there are lower molecular curves underneath, because as I've said, rubidium has a low ionization energy, so we have charge transfer asymptotes below our entrance channel, and they all connect to molecular curves. So we come in here on this curve, and then one can see that one has a crossing with another molecular curve, and here at these crossings, the system can hop over non-adiabatically to the other curve, and then when the reaction partners depart again, we end up in this asymptote where the charge has migrated from one species to the other. So this is non-adiabatic charge transfer and explains the rubidium ions. But there's more that can happen. So we can emit photons to the lowest curve, and then when we populate a continuum state associated with the lowest curve, then we have radiative charge transfer. So it's a radiative process, because we then end up also in a charge transfer asymptote in the end. Or if we populate a bound state on this curve, then we form a molecular ion, calcium rubidium+. And that explains the formation of these molecules that we see here. Now, the rubidium+ is, the rubidium 2+ is probably due to consecutive reaction of these